Okay, we are in Unit 7. This is Notes 3. So this is Volumes of Solids of Revolution. That's what it's called, and you'll see why when we introduce this to you. So I'd like to start with a similar curve to where we started with our last section. In our last section, I told you we're going from x is equal to a and to x is equal to b over here, and if you recall, we had like a curve that looked something like that, and we called that one f of x, so that's f of x. And then this one down here, that little curve there, I'm going to call that g of x. So these like continue, but that one is f and one is g of x. Okay? All right, and we'll say that this here is x is equal to b. I got a little bit off. Anyway. All right. So there's our region. Okay? There's our region. Now I want you to imagine that region revolving around the x-axis. Revolving around the x-axis. So take this, think of it as cutting it out of a piece of paper and then just revolving it around the x-axis. And if you think of it going really fast, you can visualize a solid that's formed from that. And that's what we're talking about with a solid of revolution. Okay? So I'm going to try to draw this. Sometimes it happens and sometimes it doesn't. But when you draw this and we flip it around, I'm going to draw it kind of like this. It's gonna, when it flips to the other side, maybe like that, and then this one would look more like that. When you flip it around, when you revolve it, like this is going to rotate here, and we're going to have like that. Like that. You see that a little bit? And on the inside, it's like open. On the inside, it's open, isn't it? So that inside piece is kind of open. And then it has like, it goes around. So we also have like these outside ones too. The more I draw, the messier it looks. So I'm going to kind of stop while I'm ahead and hope that you can see it. Okay? But we do have this. You can imagine what that looks like, okay? It's a solid, and then it has that opening there of clearness, right? We want to be able to find the volume of that solid. And really all we know are cross-sections. So let's take a cross-section of this, perpendicular to the x-axis. Since we revolved it around the x-axis, let's take a slice perpendicular to the x-axis. So if I do that, if I take this slice, I'm going to try to draw one slice. I think I'll draw with my pen first. So if I draw this one slice, I'm going to have that on the outside, and then I'm going to have this inner slice here, right? Can you see that? Or maybe I should have done that with a different color. Oh well. There's my slice. Okay? So it's like, for those of you who know what a washer is, it's like a little washer. A washer, I think of it as on a faucet, on the inside of a faucet. It kind of keeps everything in place. Anyway, it's a little washer. Okay, now we're going to give that washer, and so that, we can find the area of that washer, can't we? Can we find the area of that washer? Yeah, because it's a circle minus a circle, isn't it? It's a circle minus a circle, correct? So yeah, we can find the area of that whole thing. And then if we give this washer a little bit of thickness, then we can find the volume of that washer. The thickness is going to be delta x, right? Thickness is going to be delta x. So the volume of just that one washer would be the area of the big circle minus the area of the little circle, right? Because we don't want this inside because it's clear. It's not part of our solid. So we want the area of our big circle minus the area of our little circle. So we want area of the big circle, I'm going to call capital R our big radius, pi r squared, minus the area of our little circle, pi little r squared. How about that? So that will be just the area, and then we will multiply that by the thickness to get volume, right? This is area times our thickness will get our volume, right? Now we're going to take those, here's one, there's one washer, right? There's one washer, but now we need to add up all of our washer from 1 to however many washers we have, and then we let the number of washers go to infinity, right? And that gives us the integral from A to B, because we're starting at A, going to B, of pi times the big radius squared minus pi times the little radius squared dx. And this is our formula, our general formula. Okay? Big R and little r can have x's in them. They don't have to have x's in them, but they can have x's in them. Oftentimes they have x's. Let me put it that way. Okay? So here's our formula. All right? And I say formula, but it makes sense. Big circle minus little circle, give it some thickness. That's all it is. Area times the thickness. Our volume is still just area times thickness. Okay? All right, let's look at some examples. So let me you pull out your example sheet, and I will pull out my example sheet. And we'll see what we're doing here. Okay. So in general, you can put up at the top, volume is equal to integral A to B of pi big R squared minus pi little r squared dx. That would be if you're revolving around like something like the x-axis, so something horizontal. This is a horizontal axis of revolution. Okay? But what if you're revolving it around a vertical axis of revolution, like the y-axis? Then I'm going to call this C to D because we're going to need some y values there. This is still going to look the same, except we'll have a dy in here, and the r's now should have y's in them, right? Most often. And this would be for a vertical axis of revolution. Okay? Now, sometimes we see this pi, since it's in common, we see it factored out and put outside. I like to leave it inside because then it drives home the fact that we are finding the area of a circle. Area of a circle, area of a circle. Oftentimes when kids start bringing the pi out, they lose that fact. After you do lots of problems, they just lose the fact. And then they just start memorizing a formula with r's in it, and they forget where it came from. Okay? Area. That's what I need you to know. Okay? All right. Number 1, find the volume of the solid formed by revolving the region enclosing y equals 2x, y equals 0, that's just the x-axis, and x equals 3, that's a vertical line, about, and then they're going to tell us different scenarios. Now, in your notes packet, I gave you these boxes for you to sketch a graph. The graph is just for you. You may not need a graph. Once you do a few of these, we may not need it on all of them, but I will still put it on all of them. So this is the sketch of the graph is just for you. I need to see your integral and your answer. That's what I need to see, okay? So let's sketch a graph. So we're going to revolve this region around the x-axis, and I know I'm at one of my boundaries is the x-axis and one is x equals 3. This is a line starting at the, or going through the origin with slope 2, right? So when I draw this, I'm going to draw most of it over here because we're revolving this around the x-axis. I want to give some room under the x-axis to revolve this, okay? So y equals 2, x equals 3. Let's put that x equals 3 out here, okay? When I know we go through the origin, and then when x is 3, y is 6. So let's just call this 6 up here. It doesn't have to be to scale, right? Let's call that 6. So this line looks like this. Okay, that's what that line looks like. Y is equal to 2x. Y equals 0 is one of my boundaries. And then y equals 3. Missed the mark again. Y equals 3 is one of my boundaries too. So here's my region. There's my region. And let me grab a pencil real quick. I kind of like to shade my region a little bit. Just on this first one, I'm just going to shade it a little bit, just a hair. So there's the region, okay? And we're going to revolve that region around the x-axis in this case. So the x-axis, so it's going to flip around, do this, and it's revolving, so it looks like this. Okay? You don't have to draw it like that, it's okay. Alright? So in this case, when we revolve it, do we have a blank hole? Do we have something to subtract out? No, we don't. So little r in this case will be 0 because we don't have a little radius to subtract out. We just have a big radius. And what is that radius? What is that radius? Well, the radius will be this top minus the bottom. So what's what we do? Here's a representative circle in there. Top minus bottom. So that's that line 2x minus 0, right? So 2x minus 0, which is just 2x. Okay? So the volume will be, oops, I almost put v equals. Well, I'm just going to go ahead. V is equal to the integral leftmost x is 0, rightmost x is 3, pi times big R squared dx. Okay? Calculator time. We need the integral, Math 9, 0 to 3, pi times 2x squared dx. And we get 113.097. Now, if this is multiple choice and the answers have a pi in them, just take your answer, divide out that pi, and that tells you that 36 pi is equal to 113.097. Okay? All right. Next up, we're going to take the same region, but this time we're going to revolve it around the line y equals 6. Y equals 6 is way up here. So I'm going to draw my region down a little bit. There's my region. Once I draw it the first time, since we're using the same region in all of these, I'm going to just keep that. I don't have to take much time to sketch that, right? Okay, so this time we're revolving it around y equals 6. We're revolving it around y equals 6. So this piece is going to revolve and be up here. This piece, when we revolve it, it stays right there, right? But this piece revolves and goes up there, right? This piece revolves and goes up there. So we have kind of a flat line up there, and then this piece revolves like that. So we have a cutout this time? We do. We do have a cutout this time. So, all right. When you're finding your radius, I want you to always use your given region. Don't try to go up and use the one that you sketched when you revolved it. Always use your given region down here, okay? So always do that. Now, we want the big radius. We want the big radius first. So the big radius is that long. There's your big radius. What is that length? What is that length? Well, that length is 6, and that length is never going to change. It's 6 minus 0, right? What is the length of the little radius? The little radius is right here, isn't it? Little radius is right there. So this is your big radius, this is your little radius. How long is your little radius, the one that you're subtracting out? Well, the little radius is the top minus the bottom, right? So it is 6 minus that line 2x. 6 minus 2x. Okay? So when you're finding your big R and your little r, you're always going to think about your axis of revolution. Think about your axis of revolution. You're always going to be going from your axis of revolution to the far side of your region to get your big R. From your axis of revolution to the close side of your region is the little r. If we talked about it like that for our first example, here is our axis of revolution, right? To the far side of the region is our big R, and the close side of the region was on our axis of revolution. That's why there was no little r, right? But in this case, we did have a little r. We did have some white space. So our volume will be the integral still from 0 to 3, 0 to 3, of pi times big R squared minus pi times little r squared. Okay? Now if I might just want to go ahead and pull out that pi now. So I'm going to do pi Math 9, 0 to 3, 36 minus 6 minus 2x squared dx. Okay, and this turns out to be 226.195. If I wanted that in terms of pi, I just would divide out that pi 72 pi. Okay? All right. Now I'm going to start showing you how I really do these. Okay? Well, I do it the same way, but I don't always draw this 3D picture. Okay? Let's revolve this around the line y equals 8. So I'm going to draw my region. Draw your region. Sketch. Just a quick sketch. Don't get too fancy about this, just a quick sketch. There is your region. Now I want you to sketch your axis of revolution. Where is your axis of revolution? Y equals 8 is up here above. So do a dotted line on your axis of revolution. Okay? From your axis of revolution to the far side of your region is your big R. from your axis of revolution to the close side of your region is your little r. Now just find the length of your big R and little r. The length of big R is always a constant, isn't it? It's always a constant, and it's always 8. The length of little r will be 8 minus 2x, because this is y equals 2x right there. So 8 minus 2x. Okay, I get this a lot. Miss Mary, how do you know it's 8 minus 2x and not 2x minus 8? And to answer that, I would go back to this. If you are on, if you have a curve here and a curve there, if this is y is equal to 8 and this is y is equal to 2, what's the length? You're not going to say the length is 2 minus 8, because you're going to get a negative. You always go from high to low if you're looking at a length, if you want the length. And that's what we want here. We want the length. So the length is always the top minus the bottom. Whatever is on top minus whatever is on the bottom, in this case 2x. The volume will be the integral 0 to 3 still, of pi times big R squared minus pi times little r squared, area minus area. Okay? And then when you go and put that into your calculator, and I'm going to stop putting that in my calculator, but when you go put it in your calculator, we get 339.292, which is 108 pi, if we want it in terms of pi. I'm going to stop spending the time to put that in my calculator, I should say. Okay. Let's take the same region and this time revolve it around the y-axis. This time revolve it around the y-axis. So here's our region. Remember, this was 6 right here. Okay? This time we're revolving it around the y-axis. So remember, draw the axis of revolution with a dotted line. So draw that with a dotted line. It's hard to draw it right on the axis, but you get the idea. Okay? From the axis of revolution to the far side of your region is your big R. From the axis of revolution to the close side of your region is your little r. Now find those lengths. Okay, since our lengths are horizontal, we're going to have a little delta y. We're going to our washer would be perpendicular to the y-axis this time, right? So we're going to need a delta y. If you need a delta y, then we need for our curve here, we need for our y is equal to 2x to be x equals something. So we had y is equal to 2x, and we're going to need to use x is equal to 1/2 y, or y over 2. Okay? So vertical axis of revolution means you need a delta y or a dy. Okay? So get all y's for your curve. So this is now x is equal to 1/2 y instead of y is equal to 2x. Okay? What is big R? What is big R? Well, big R is a constant, isn't it? And it's always 3 units long. So big R is 3. What is little r? We need to go from the right to the left, don't we? So 1/2 y minus 0. 1/2 y. Okay? So the volume will be the integral from, okay, what are our extreme y values? What's the lowest y value of our region? Of our region, the lowest y value is 0. What's the highest y value of our region? 6. So we need to go from 0 to 6. And then we have pi times big R squared minus pi times little r squared dy. That goes into your calculator, and your calculator spits back 113.097, which is still 36 pi. Okay, let's take the same region and revolve it around x equals 3. X equals 3 is still vertical, isn't it? So here's our region. And this time our axis of, draw a dotted line, axis of revolution is right at x equals 3. Okay, from the axis of revolution to the far side of your region is your big R. From the axis of revolution to the close side of your region is your little r. Well, our axis of revolution is right on our boundary, so little r is 0. Okay, big R, we need that length. What is that length? Well, the length will be x equals 3 minus x equals y over 2. So 3 minus 1/2 y, or y over 2. So the volume will be the integral from 0 to 6, because we're on y's, of pi times big R squared dy. That goes in your calculator, and we get 56.549, which is 18 pi. Same region, this time revolve it around x equals 4. Well, x equals 4 is out here somewhere, right? From your axis of revolution to the far side of your region is the length of big R. From the axis of revolution to the close side of your region is your little r. Little r here is always 1, 4 minus 3. Big R will be 4 minus y over 2. 4 minus y over 2, or 1/2 y. Okay, so the volume is integral 0 to 6 of pi times big R squared minus pi times little r squared dy. Into the calculator that goes, and we get 113.097, which is still 36 pi. Love these. Okay. Example 2. New code. Find the volume of, if the region enclosing y equals x squared, that's just a parabola, right? That's a parabola. Y equals 0 would be your x-axis, and x equals 2 would be over here, right? So we're looking at that little region right there, and then we're going to revolve it around some different things. So I'm going to draw that region, and I'm going to draw it so that I can revolve it around the x-axis. So the region looks like that. That's our region. And then we want to begin by revolving it around the x-axis. From the axis of revolution to the far side of your region is your big R. From the axis of revolution to the close side of your region is little r, which in this case is 0 because it's just not there. Our region is on our axis of revolution. Big R is the top minus the bottom, so it's just x squared. So our volume will be the integral from, okay, where is our boundary here? This is 2, this is 0, so 0 to 2, right? Of pi times r squared, pi r squared, area of a circle. All we're doing is cross sections are circles today. That goes into your calculator, and it spits back 20.106, which is 32 pi over 5. Okay. Next up, we're going to take the same region and revolve it around y equals 4. Well, y equals 4 will be on the y-axis. Let's see where at. If we put 2 in for x here, we do get 4. So this is the point 2, 4. So over here, y equals 4 will be right here. Okay? Big R from the axis of revolution to the far side of your region. Little r from the axis of revolution to your close side of your region. Every time is the same. So big R is 4 minus 0, so just 4. Little r is 4 minus the curve x squared, so 4 minus x squared. So volume is integral 0 to 2 pi times big R squared minus pi times little r squared dx. This is where you need to be very, very careful putting it in. When you have x squared and then it's all squared, be careful putting that in your calculator, okay? This gives us 46.914, which is 224 pi over 15. Okay? Now we're going to revolve. We're going to revolve this around y equals 5. Well, y equals 5 will be up here above the region, right? From your axis of revolution to the far side of your region is your big R. From the axis of revolution to the close side of your region is your little r. Big R is always 5. Little r is 5 minus x squared. So the volume is integral 0 to 2 pi times big R squared minus pi times little r squared. Again, be careful with that. And we're going to get 63.670, which is 304 pi over 15. Okay, moving right along on a roll here. Same region. This time we're going to revolve it around the y-axis. So same region. This time we're revolving it around the y-axis, which is, of course, vertical. Vertical, so therefore, let's go get a delta y. So if we're getting delta y's, then everything has to be in y's, right? Our curve was y is equal to x squared. It's no longer going to be y is equal to x squared. It's going to be x is equal to the square root of y. Why did I not take the negative? Because the negative would be over on this side, and we only want this side. Okay? All right. So what's big R? Well, big R is from our axis of revolution to the far side of your region. That's your big R. Little r is from your axis of revolution to the close side of your region. That's your little r. Now you just need those distances. So what is big R? Big R is always 2. Little r is the curve minus 0, so just the curve, square root y. So our volume is the integral from the lowest y value is 0. What was that highest y value? That highest y value was 4, right? Because that point was 2, 4. So we're going up to 4. Okay? And pi times big R squared minus pi times little r squared dy, dy this time. Okay, this turns out to be 25.133, which is 8 pi. Okay, what if we took the same region and revolved it around x equals 2? That would be right here, right? X equals 2 would be right here. It's still vertical, so we still need a dy because our slices will be going towards the y-axis, right? So, from the axis of revolution to the far side of your region is big R. Little r here is 0 because our region lies right on our axis of revolution. So a big R will be 2 minus square root of y. 2 minus the curve, right? Always go right minus left or top minus bottom, always. So the volume will be the integral from 0 to 4 again, pi big R squared minus pi little r squared dy. This turns out to be 8.378, which is 8 pi over 3. Okay, same region. Let's revolve it around x equals 4. Same region. X equals 4 is way out here, right? From your axis of revolution to the far side of your region is your big R. From the axis of revolution to the close side of your region is your little r. Little r here always has length 2, 4 minus 2. Big R has length 4 minus that curve, so 4 minus square root of y. So the volume is the integral from 0 to 4, because of this 4 up here, of pi times big R squared minus pi times little r squared dy. And the calculator told me that that was 41.888, which is 40 pi over 3. Okay, example 3. Hopefully you're seeing the repetition in this. This is not hard stuff. It's interesting when you think about what we're doing each time. We're going through these really fast, but what we're doing each time is pretty impressive. Finding these various volumes of these solids formed by revolving a region around some axis. Okay, new problem. Okay, the region is formed by, it's bounded by these curves. So 1 plus square root of x. I know what square root of x looks like, and we're adding 1 to it, so it's going to be the square root function just shifted up 1, right? Y equals 1, that's a horizontal line. X equals 4 is a vertical line, and then that's our region. Okay, so let's think about this. I have my, I'm just going to draw it here. Square root of x. X can only be positive, so I probably shouldn't have drawn anything over here. X can only be positive or 0. So when x is 0, y is 1. When x is 1, y is 2. When x is 4, y is 3, and so forth. So we have this square root function, something like that. I'm going to stop when x is 4 here because that's one of my boundaries. So when x is 4, I'm at a boundary, and then one of my boundaries is y is 1, so that's a boundary. So find your region. Take a moment to find your region, especially when you have several questions asked about that. So this is 4. We will likely need this point up here. So what is that point? When x is 4, that is going to be 3. So this is the point 4, 3. Okay? Now we're going to revolve this around the line y equals 3. Well, y equals 3 is all the way up here. I should have really put my graph down lower, but that's okay. Whatever. Okay, there's my y equals 3. Draw your big R. There's your big R. And draw your little r. There's my little r. Big R is always 3 minus 1. So big R is always 2 here. Little r is 3 minus the curve, right? And we are doing a delta x because we get to do these vertical lines for our little slice, for our radius, right? So they are going to have a little delta x. So we are back to delta x. So 3 minus the curve. So 3 minus 1 plus square root x. Be careful with your signs there, right? So the volume will be the integral from, we're on x's, so what's your leftmost x? 0. What's your rightmost x? 4. Pi times big R squared minus pi times little r squared, be careful with that, dx. Into the calculator that goes, and it spits out 41.888, which is 40 pi over 3. Let's do the same thing and revolve it around the line y equals 5. So same region. That should look more like that. Whatever. Y equals 5 will be up higher, right? Big R, little r. Big R is 5 minus 1, so 4. Little r is 5 minus the curve. So the volume will be the integral 0 to 4 of pi times big R squared minus pi times little r squared dx. 108.909, which is 104 pi over 3. What about x equals 6? X equals 6. There's our little region, and this was 2, right? Oh, I'm sorry, this was 4. That was 4. So x equals 6 will be out here, like that. From your axis of revolution to the far side of your region, and all of a sudden I see I need a delta y. This is a delta y one because we're going to, we're going horizontally for our slice. There's our big R. Here's our little r. I need delta y, so I need all x equals. So come to your curve and solve it for x. Square root of x will be y minus 1. Square both sides. So x will be y minus 1 squared. Okay? So big R will be 6 minus the curve. 6 minus y minus 1 squared, the curve. Little r will be 6 minus 4, which is 2. So the volume will be the integral from, from what to what? We need y's, right? What is my lowest y value? My lowest y value was 1 here. And what was my upper y value? That was at 3. So from 1 to 3, pi times big R squared, that's one that would be a little tricky to type in, so take your time, minus pi times little r squared, dy. That turns out to be 120.651, which is 192 pi over 5. Okay, one more example, three-part example. This time we're enclosing y equals x cubed. We know what y equals x cubed, I'm sorry, that's a squared, never mind. Y equals x squared, we know what that one looks like, it's a little parabola. And the cube root of x, looks like this. Let me get a different color here. Cube root of x looks like that. Okay, so where's our region? It's right here, this little like eye-looking region. Okay, so when I draw it, I'm just going to draw that little piece. So it does this. Okay, it does that. Now we're going to need to know like which curve is which. So which curve was which? The bottom one was our x squared curve, and the top one was our cube root of x curve. Okay. All right. Dotted line on the axis of revolution every time. Dotted line, axis of revolution. From your axis of revolution to the far side of your region is your big R. Axis of revolution to the close side of your region is your little r. So big R here is the cube root of x minus 0, which is just cube root of x. Little r is x squared minus 0, which is just x squared. So the volume will be the integral of, the integral from, what's our leftmost x value? Definitely 0. What's our rightmost x value? Where do they intersect? Where do those intersect? Where does x squared equal the cube root of x? At 1, right? They intersect at 1. You have a calculator, so you can always go and find that out. Okay? Pi times big R squared minus pi times little r squared dx. I am going to put that on my calculator because I want to make sure you guys can do this one. So grab your calculator and make sure you can do this one. Math 9, 0 to 1, pi times the cube root of x squared is going to be, I'm going to type in x to the 2 over 3. Remember the 3, the root is the denominator of your exponent. So that's the big R squared minus pi times, what is x squared squared? X to the 4th. Or you can put x squared squared, that will work as well, dx. And we get 1.257, which if we divide out that pi, oops, not e, divided, answer, divided by pi, we get that, there's a little bit of an error here, but 0.4, so 5, this turns out to be 2 pi over 5. That's the 0.4. Okay? All right, same region. This time about the y-axis. So y-axis. When you draw your big R and when you draw your little r, you see that they are horizontal. So we need a delta x. We need a delta y. We need y's, right? So take each of your curves and quickly solve them for x. Okay? This curve now is that was the cube root. So when you solve that one for x, we're going to get y cubed, right? This curve was x squared. So that's going to be, when you solve that for x, you're going to get the square root of y. So big R is square root of y minus 0, so square root of y. Little r is y cubed minus 0, so y cubed. The volume will be the integral from, okay, what are my y boundaries? 0 is my lowest y boundary, and my upper y boundary is still 1, right? Because 1 squared is 1, cube root of 1 is 1, so it's still 1. Pi times square root of y squared minus pi times y cubed squared dy. Into the calculator that goes, and we get 1.122, which is 5 pi over 14. One last example. Let's take this region and revolve it around y equals 1. Y equals 1. There's y equals 1. Big R, little r. Right? We're back to these vertical lines, so we're back to delta x. We're back to delta x, so back to our x's, right? Big R is 1 minus, that was our x squared curve, right? 1 minus x squared. Little r is 1 minus the cube root of x. So our volume is the integral from 0 to 1, pi times big R squared minus pi times little r squared dx. This turns out to be 1.361, which is 13 pi over 30. Right. Very good. Okay, now it's time for you to go practice.